We're going to finish off our last day of new stuff in this unit by talking about two concepts, the first of which we call the generator effect. You guys learned way back at the beginning of this unit, or at least near the beginning of this unit, about a discovery that was made almost 200 years ago. I said it was perhaps the most important technological discovery ever, or certainly one of the most important technological discoveries ever. That discovery was Ørsted's discovery in 1819 that electric current, or just moving charges, generate magnetism. That's a big deal, and that happens every single time you have an electric current. We will always get a magnetic field, a circular magnetic field that surrounds the moving charge that's part of this electric current. Well, the generator effect is kind of the opposite of that. The generator effect says that magnetic field can produce an electric current. Physics is a really symmetrical subject. If A will cause B, then usually B will cause A. If electric current will generate a magnetic field, then a magnetic field might be able to generate an electric current. The only little trick to this is to recognize that this always happens, that an electron or whatever charge that's moving forming the electric current will always cause a magnetic field, and the magnetic field will sometimes cause an electric current. Not always. There are conditions on this, whereas this just always happens no matter what. The generator effect is this effect right here, that a magnetic field will cause an electric current, the production of electricity by magnetism. It was discovered 12 years after Ørsted's discovery in 1831. And it was discovered by two guys, independent of one another. Michael Faraday was an Englishman, Joseph Henry was an American. They both, around the same time, just happened to notice that, hey, if we do something to a magnetic field, then that magnetic field can cause an electric current. Talk about important scientific discoveries. The Ørsted's discovery was a big discovery, but this was almost as big, maybe as big. This is how we generate almost every bit of electric current we have today. Electromagnetic induction, the generator effect, the idea that magnetism can cause electricity. I said there are three conditions. One of these three conditions has to be met in order for electricity to be produced by magnetism. The first one is, look, you got a wire, you got a magnetic field, you move the wire. Okay? My hand is going to represent the magnetic field. This board marker is going to represent the wire. Okay, if I've got a magnetic field and a wire and they're just sitting there like this, nothing happens. But as soon as I move the wire, one way or the other, or back and forth, then I'm going to generate an electric current in the wire. The second, once again, I got a wire and a magnetic field. This time, instead of moving the wire one way or the other or back and forth, this time I'm going to move the magnetic field one way or the other or back and forth. So bottom line is, first two conditions say that if you got a wire and a magnetic field, you got to move one of them. It doesn't matter which one, they got to move relative to each other. I said a few minutes ago that this is the concept behind just about every bit of electricity we generate today. The exceptions might be batteries. And although we usually recharge batteries nowadays by using electricity that comes from our wall, which most of it comes from this principle. The other exception would be solar power. Okay, we generate electricity by solar power in a completely different way than the generator effect. But in Alberta, most of the energy that we use, most of the electrical energy that we use is generated by burning coal. So how does that produce electricity? Well, when you burn coal, it produces a lot of heat. That heat boils water. That boiling water creates steam. That steam rises and turns a turbine. And really what a turbine is, it's wire that moves as it turns relative to a magnetic field generates a current in that wire. In Ontario, they generate some of their power by hydroelectric dams. They've got this big lake behind a dam, and the water falls through this penstock to this turbine in the hydro dam. Turns a turbine. The falling water turns a turbine. That turbine is basically wire that moves through a magnetic field and generates electricity. In Ontario, they also use nuclear power. How does that work? Well, you split the atom, which generates a huge amount of energy, but it's in the form of heat. That heat boils water, it creates steam, it rises, and then it turns a turbine just like it does in a coal-fired power plant, except it just generates a lot more heat in a nuclear reaction than it does in the chemical reaction of burning coal. Just about every bit of electricity we generate is generated by either moving the wire through a magnetic field or moving the magnetic field relative to the wire. So why does this happen? I'm going to give you a little paragraph to describe why it happens, but then I'm going to give you a picture on the next page to kind of clarify this description. Basically what happens is you move a wire, the electrons will start moving because of what we call a motor effect force. Motor effect force, although we may not have called it that before, we've done it. A motor effect is when a charge experiences a force because it's moving through a magnetic field. Now, that's not going to make sense to you right now why we generate a current this way, but it will when you see the diagram. Because of this motor effect force, they accumulate at one end of the wire, but if the wire is connected to a circuit, then they end up flowing around the circuit. And you power up the light bulb, or you power up the electricity grid, or you charge your iPhone, or whatever it is that you're trying to do. So here's a picture that's going to describe what we just gave you in paragraph form here. What I want to do first, though, is scratch out some stuff, okay? I don't want you to see any of this stuff. Right now, what do we have? We got two magnets. Each of them have a north pole and a south pole. There's a wire in between those two magnets. So that wire will experience a magnetic field, but nothing's going to happen to that wire right now because wire's probably made out of copper. It's not ferromagnetic. Nothing's going to happen to it. There's electrons in that wire. We've got one of those electrons drawn. It's still nothing happens to it. If that electron is stationary, it would be affected by a gravitational field, by an electric field, but not by a magnetic field if it isn't moving. Let's get it moving. Let's get it moving as part of the wire upwards. We're pushing the wire upwards. Maybe we're physically taking the wire with our hand and pushing it upwards. Maybe it's rising because steam is rising below it, pushing it upwards. Maybe whatever. It doesn't matter how it's moving upwards. It's mechanically being pushed upwards. So that wire moves upwards, and as it does, the electron or the electrons inside that wire move with it. This is not an electrical or a magnetic phenomenon. It's a mechanical thing. We are pushing the wire up. Now, there is a magnetic field here as well. That magnetic field points from the North Pole to the South Pole. Now look at what we've got. We've got a wire that's moving upwards through a magnetic field because we push it upwards. Therefore, we've got an electron or multiple electrons that are also moving upwards through a magnetic field. Not because of magnetism or electricity or because of anything else, but because we pushed the wire. But the bottom line is there's an electron or electrons moving upwards. Yep. Right here. That's a B for magnetic field. So the electron is moving upwards. Now, we're going to use a hand rule for deflection to see what happens to it. Hey, think about what's happening here, right? We've got an electron moving upwards like this through a magnetic field. That experiences a magnetic force. So we're going to say thumb in the direction that the particle is moving, which is because the wire is moving upwards, the particle is moving upwards with it. The magnetic field goes from north to south. There's a magnetic force on that electron. We call it a motor effect force or a magnetic force that pushes it out of the page. In other words, The electron that is moving upwards because we pushed it upwards experiences a magnetic force along the length of the wire. So it starts moving along the length of the wire. Now we've got an electric current, right? We push the wire upwards, the electrons start flowing through the wire along the length of the wire. That's an electric current. Remember what we said we needed for an electric current to be generated here? We had to have a wire, a magnetic field, and we had to move one of them. And because of that, there's a motor effect force on the electron, or a magnetic force caused by hand rule for deflection on the electron, which causes the electrons to start flowing along the length of the wire. This diagram down here just shows us the hand rule that I just illustrated. That make sense? So essentially what we're saying is that almost all the electricity we generate, with the exception of a battery and solar cells, is generated by a motor effect. Once again, fundamentally based on what Oersted taught us in 1819, that electric currents generate magnetic fields. Okay? We don't have that discovery, then we don't have a motor effect, a hand rule for deflection. We don't have that, then we're not going to get electricity generated from this magnetism. All right? Yep. The question, if you didn't hear it, was effectively, and I'll just paraphrase it here, you move this wire upwards, and then at some point you stop moving it upwards and you start moving it downwards. Okay, maybe it's because, I don't know, you couldn't reach it anymore and gravity pulled it down, or whatever the reason. Maybe it's because it's some kind of cyclical thing. Bottom line is you got a wire moving up, and then you got the wire moving down. When you move the wire downward, isn't the current going to reverse in there? Yes, it will. Because the hand rule is going to have my magnetic force going into the page instead of out of the page. Isn't that going to cancel things out? No, it isn't. What it's going to produce is what we call AC current, alternating current, which is what we have in our houses. Current that goes one way and then stops and reverses direction and goes the other way. Keeps going back and forth, back and forth, back and forth. That's what's happening in the wall of this room right now. It's currents going back and forth, back and forth, back and forth. They don't cancel each other because they're at different times, right? It's going this way as the wire is moving upwards. And if for whatever reason I start moving the wire downward, maybe it left the magnetic field and I want to keep it in, so I push it back down, then the current would start going in the opposite direction, and so on. Is that all right? Make sense? So if we reverse the movement, it reverses the current as well. The demonstration that we just did is going to use what we just learned that Faraday and Henry taught us, this whole idea that electricity is produced by magnetism, but it's also going to use what Oersted taught us before that, 12 years before that, in that electricity generates magnetism. The idea that electricity generates magnetism and that magnetism generates electricity. The first part of it is that magnetism generates electricity. That's Faraday, right? We had a magnet in our hand, or at least most of us had a magnet in our hand. Mac didn't. Mac just had a piece of steel in his hand. Okay, but most of us, as we were dropping something through this copper tube, dropped a magnet. So we had a magnet that was moving relative to a conductor. And what happens there? Well, we learned from Faraday, 1831, that when you've got a magnet and you've got a wire and you move one of them, you generate a current. So there is an electric current, albeit a very small electric current, generated in this copper tube when I drop the magnet through. We've got a magnetic field. We're going to call it magnetic field number 1, generates an electric current in that copper tube. This is nothing new. This is what we spent the last few minutes before our demonstration talking about. The discovery by Faraday that moving magnets in a conductor will generate an electric current. But let's rewind a little bit. Oersted in 1819 told us that an electric current generates a magnetic field. So we had a magnetic field that we're dropping. It generates a current, but the current that was just made by the first magnetic field generates its own magnetic field. We're going to call it magnetic field number 2. Now we got two magnetic fields, right? We got the original one that we all dropped through the copper tube, through the conductor. And now we have a second magnetic field that was produced by, we didn't have originally, it was produced by the current that came from the original magnetic field. So it's kind of like the second one ultimately comes from the first magnetic field, but it's not the first magnetic field, right? The first magnetic field is a magnet that we dropped. The second magnetic field is the one that was generated by the current that was generated by the first magnetic field. This is Ørsted. Now we get two magnetic fields. Two magnetic fields, the original and the one that was produced by this electric current. These two magnetic fields will always act to oppose the motion. Whenever we have two magnetic fields, there's going to be an interaction between them. Maybe they attract, maybe they repel, maybe they help the motion, maybe they oppose the motion. Well, these two magnetic fields will always oppose the motion. In other words, if gravity is pulling down on this magnet, then the magnetic force will push up to oppose the motion. If you're pushing on the magnet to the right, then there'll be a magnetic force to the left. If I throw the magnet up into the air through a coil of wire, then there'll be a magnetic force downward that opposes the motion. The two magnetic fields have to do something. It can't cause the motion to be helped because that would violate the law of conservation of energy. Think about that. If I drop this magnet through this copper tube, it should, we would think, would accelerate at 9.81, but the magnetic force, second magnetic force, causes a force with the first magnetic field. It can't cause it to accelerate at 15 meters per second squared. Otherwise, you end up with more energy at the bottom than you started with at the top. You've created energy. You've violated the law of conservation of energy. So if there's going to be a force, it can't be a force that helps it. It's got to be a force that hinders it or opposes it so that we don't violate the law of conservation of energy, so that we don't create energy from nothing. That's how I knew when we did the demonstration, as long as I had the right thing in my hand here, I knew that the magnet would accelerate downward at a much lower rate than the piece of steel would accelerate downward. This happens with a magnet, but when you drop a piece of steel through there, what's missing? The original magnetic field. If you don't have magnetic field number one, then you don't get a current produced. If you don't get a current produced, you don't get magnetic field number two. And if you don't have two magnetic fields, they don't interact with each other to oppose the motion. So what happens? It just falls at 9.81 meters per second squared, like it did for Mach every time you tried it. On the board right now, you see a coil of wire or a solenoid with, we have a piece of steel inside it. It doesn't really have to have a piece of steel inside it. I'm just drawing it that way just because. It could just be the coil wire, that would be fine. There's no current going through this coil of wire right now. In fact, there's not even a battery attached. The thing at the bottom is a light bulb. That light bulb isn't going to be turned on because there's no current. You can hook up a light bulb to a wire all you want. If you don't put a current through the wire, the light bulb is not going to light up. I'm going to put a magnet over here on the left-hand side. This magnet is going to have a south pole and a north pole. Okay, whatever the polarity of the magnet is, okay, there we have it. We're going to move that magnet to the right. So its velocity is to the right. We're pushing it to the right, or something at least is pushing this magnet to the right. We know by Faraday that when we move a magnet relative to wire, we're going to generate a current in the wire. There's going to be a current in this wire, and that light bulb will go on. Now, which direction is the current? We don't know that. Okay, but we know there's going to be a current in the wire. We know by Ørsted that that current will generate a magnetic field. So this piece of steel inside this solenoid is going to become magnetized. It's going to develop a north pole and a south pole. And we know, according to Lenz, that this magnetic field that was just made has to act together with the original magnet to oppose the motion. So Although we don't know which way the current is pointing, we do know the polarity of this new magnet, magnet number 2, the one that was just generated. Which end is north, which end is south? Left side, north or south? South? Left side is north. How many people agree with that? Okay. I'm going to go the other way and say that end is north. Why am I saying that end is north? Well, if I'm moving this magnet, the green magnet, bringing it over to the right, and I want to oppose its motion, then I have to repel it. That make sense? If I'm attracting it, then I'm not opposing motion. I'm going to pull it over to the right even faster, right? Make sense? Got to have a like pole in order to repel it. Got to have a force of repulsion in order to oppose the motion. Now, we still don't know which way the current is pointing. We know that there's going to be, the light bulb is going to turn on here because there is a current. We just don't know which way it goes. So let's take out our little manipulative that we made here earlier in the unit. Let's figure out which way the current goes. Once again, this is the front. I'm going to stick my thumb from south to north inside the coil, which is going to go from the right side to the left side. So thumb goes from right to left. My fingers in front of the coil will point downwards. And that means the current in this wire points down in the front and up in the back. It ends up going counterclockwise. So by Lenz's law, we just were able to determine which way the electric current will move as a result of this electromagnetic induction, as a result of this magnet coming nearby, moving towards this solenoid. I want to draw another picture here. Same solenoid, exactly the same solenoid, exactly the same magnet, exactly the same motion. It's moving to the right, but this time it's going away from the solenoid and moving to the right. We know that it's still moving relative to the wire. We know that that's still going to generate a current in the wire. The light bulb's going to turn on, and there's going to be a magnetic field produced as a result of that current. It's going to give this solenoid a polarity. We know that that solenoid has to act, this new magnet that was made in this solenoid, has to act to oppose the motion of the original green magnet. Which end is going to be north? Which end is going to be south? Left side, north or south? Yep. South. This is going to be north. Good. It's reversed this time. How come? Yeah, go ahead. Good. In Lenz's law, I never said that it's got to be a repulsive force. I said it has to be an opposing force. If it's moving towards it, it has to repel in order to oppose it, right? If it's moving away from it, it has to attract it back in order to oppose the motion. So this time, we've got a magnet that's set up opposite to the one that's above. This time, take our little manipulative. We stick our thumb from south to north, from left to right. Our fingers are going to point up in the front, up in the front, down in the back, up in the front, down in the back, and so on, so that this time the current would be counterclockwise. That make sense? Let's try one more that's not in the context of a coil. Let's say this time we've got just a loop of wire like this, and we've got this bar, this conducting bar, that's free to slide along that, and it's touching it the whole time. So it's making contact the whole time. Let's say we're going to move this wire. We're going to move the wire this time, not the magnetic field like we moved in the last one. We're going to move the wire to the right. But there's a magnetic field that's pointing into the page. What's the direction of the current here? Well, if I move this wire to the right, there's going to be a current produced in this wire. And that current is going to generate another magnetic field. Not the original green magnetic field, but a second magnetic field that's going to act together with the original green one to oppose the motion. If I move this to the right, then there must be a magnetic force to the left to oppose the motion. Agree? I push it to the right, the magnetic force pushes it to the left. If there's a magnetic force to the left, we're not going to use the coil rule this time. It's going to be the hand rule for deflection. If there's a magnetic force to the left and the field points into the page, my thumb will point downwards. The direction of the current will be down in the part of the wire that moves, and it will end up going around clockwise. Does that make sense? So fundamentally, what does Lenz's law come down to? It comes down to two discoveries that we've already talked about. Faraday, which says move a wire or move a magnet relative to the other one, generate a current. Oersted, current generates magnetic field. Lenz, which says the magnetic field that we started with, the magnetic field that we have now, act to oppose the motion of, in this case, the magnet, in this case, the magnet, or in this case, the wire. Whatever it is that's moving, its motion is opposed. All right?